Okay, now that we're all brought up to speed on the ABCD matrix, or just the transmission matrix, a next question might be, how do I transform an impedance matrix into one of these transmission matrices? Or to think of it another way, suppose I give you some microwave circuit and you know what this matrix is here. Can I use that information to generate this matrix over here for this relationship? And the answer is actually yes. There's a very simple linear transformation you can do on these parameters here. You do some basic algebra to fill in this matrix, and it's just a little bit of algebra to get us there. So remember, this is a system of equations. I'm going to write this as V1 equals I1 Z11 minus I2 Z12. So you notice I put a negative sign here because in the context of an impedance matrix, the currents were defined as going into the network. In the context of the ABCD matrix, the currents are defined as going to the right. So that means this current here has to be negated in order to be consistent with this convention over here. So I'm also going to now write the second equation. So you just say V2 is going to be Z21I1 minus Z22I2. So I'm going to write that as I1 Z21 minus I2 Z22. So I'm just going to essentially write out the same equations representing this equation over here. So here's a system of linear equations. Here's another system of linear equations. V1 is equal to A V2 plus B I2. And then I1 is equal to C V2 plus D I2, like so. Now, given these two conventions here, these sort of definitions or these linear equations, I want to use the information here to derive these coefficients over here, A, B, C, D. So first thing we're going to do is calculate A in terms of these parameters over here. So you'll notice that A, we can define it as the ratio of V1 over V2 subject to the condition that I2 is equal to 0. Because remember, we have the power to open and close circuits at the various ports to a network. So what I can do is force I2 to be 0, and then my A would be calculated by simply measuring V1 over V2. Well, you see over here in terms of this matrix, here is V1 and here is V2 here. So we'll just write this out as I11 Z11. What? Hold on, I've got this guy here also setting to 0. So you can write out this numerator, I1 Z11, and it's technically right negative I22, but we force that to be 0, so I don't have to write anything over there. And then same thing on the denominator, I1 Z21 minus that it was set to 0, so that doesn't matter, so I'll just say 0, and then everything divides out, and you can see I get a nice clean solution, Z11 divided by Z21. Okay, so given this matrix here, I can now fill in that matrix element over there, and we just repeat the process on the other terms. For example, B is equal to, over here, I can set this guy to 0 by shorting out that port, but there could be a current there, so it would be the ratio of V1 over I2 subject to the condition that it's V1 over I2 subject to V2 equals 0. There it is, excuse me. So we'll just plug that in. Now this gets a little bit more complicated. So I can see V1 in the numerator here is equal to I1 Z11 minus I2 Z12. And then I have this I2 in the denominator like that. So this gets a little bit tricky. So what can we do to simplify here? Well, I know that this will become the following. I get a Z11 times I1 over I2 subject to V2 equals 0. And then I'm going to subtract the numerator here. So it gets a little tricky here, Z12 like that. So that little condition technically hasn't gone away. I'm forcing that there. So I1 over I2, what can we do with that little guy? Well, we look now to this equation over here. We are forcing V2 equal to 0, which then gives me a relationship between these two currents. So I'm just going to write that over here. I1 Z21 is equal to I2 Z22. Okay, so I set that to 0 and you move this term and this relation now pops out because that is the condition I have imposed by setting V2 equal to 0. Which means I have an I2 here in the denominator, so that implies I2 is equal to I1 Z21 divided by Z22. So I'm now going to substitute this into that denominator here. So what we'll get is B, so I'm just continuing my equals here. You get a Z11, and that will become I1. So this is the little tricky part, divided by I1 times Z21, and then it's divided by Z22, so that comes up into the numerator like so, minus Z12. So we'll get these guys dividing out, which gives us Z11, Z22 divided by Z21 minus Z12, which I'm now going to do a little bit of mathematical trickery and just multiply by Z21 over Z21. So I have a common denominator. And then you finally get, so there's a little bit of trickiness going on, but it's just some straightforward algebra. So I will then get Z11, Z22 minus Z12, Z21 divided by Z21. Okay, just like so. So you can then apply a similar argument to the other two terms. So we'll just skip ahead to the end with that. And we find that C is equal to, I1 over V2 subject to I2 is equal to 0, which we then do that same sort of trickery and we'll find we get just 1 over Z21. And then of course, a similar argument gives us D is equal to Z22 divided by Z21. So what that means is if I am given this information here and I want to generate this matrix over here, I just substitute in all of these results. So let's see if I can squeeze it here at the bottom. We'll have something like this. A, B, C, D is equal to, and I get the following matrix. I'm just going to plug in Z11 over Z21. And then I'll get a B, which is this guy over here. So this is the big yucky one. Z11, Z22 minus Z12, Z21 divided by, so I'm crashing into my other terms here, so be careful, over Z21. And then my C over here will be a 1 over Z21. And then my D becomes a Z22 divided by Z21. And we enclose the bracket there. So let's see if I can circle that. It's a little out of space there. So that's the substitution you need to make here. So it's a pretty straightforward argument. And all it is, again, all it says is if I am given this matrix here, which we've already seen, if I'm giving you a circuit, we can calculate this matrix. It is a straightforward little bit of conversion to create this matrix over here by using these substitutions. Okay, so that is how we convert from an impedance matrix to an ABCD matrix. If you want to go the other direction, that's probably a little more difficult, but the book doesn't really seem to think that's quite as important of a transformation to make. Okay, so keep that in mind because you can do a lot of fun and interesting problem solving with that expression there.